Hi there, during this quick session I'm going to go over the similarities between both gravitational and an electrostatic field. So just looking at the IB data booklet, okay, and this is the old IB data booklet, so not for 2006 onwards, but nevertheless the formulas which are identified show that there's a similarity in their format, and that's what I'm going to be talking about very quickly. So first of all, if you think about Coulomb's law versus Newton's law of gravity, if we Coulomb's law, we see that we have the force between two charged objects divided by which is as a relationship which is divided by r squared. When we look at Newton's law of gravity, we say a very similar structure. In this case, it's two massive objects and the force of attraction between them. We see 1 over 4 pi epsilon 0, which is the equivalent of a constant, and we see g, which is obviously the gravitational constant. The differences and similarities are Coulomb's law can be both attractive or repulsive. It's 1 over r squared relationship. It's a very strong force and only relevant on relatively local scales. For Newton's law, it is always attractive. It's also 1 over r squared. It's a very weak force in relative size, and it's important on very large scales, for instance planets and the universe. Okay. So those are my similarities and differences. Crucially, we're talking about two spheres, a charged sphere or a massive sphere. Now, if we look at electric field strength, again, we try and highlight the similarities here. Electric field strength at a distance r from point charge q, we see again a constant multiplied by the point charge divided by r squared. And the gravitational field strength, we have a constant multiplied by a point mass divided by r squared. Electric force. Force equals the charge multiplied by the electric field, and gravitational force is mass times g, which is the gravitational field strength in that location. Again, electric potential, we see a very similar situation. For electric potential, the distance r from a point charge, the potential is a constant multiplied by a point charge divided by r in this case. And for gravitational point charge, we have a constant multiplied by the mass divided by r. Again, the idea between electric potential and gravitational potential needs to be highlighted. There's lots of similar thinking here. If we look at the relationship between energy change and the electric potential difference between two locations, so that would be V. So the potential difference multiplied by the charge will give us an indication of the work done and the energy change. In the same way, the gravitational potential difference would equal multiplied by the mass will equal the work done and therefore the energy change. I always think that this is the most important formula because it links up the idea of force fields and potential fields. So what we can see here is, remember that the rate of change of the potential is equal to the rate of change of the electric field divided by mass, and that's always a very useful formula to come out with. So that's my very quick highlighting of some of the similarities between electric and gravitational